but it's not easy, you know, because one has to be prepared for the worst situation.
No, of course, for undergraduate students, when there are big lectures, then everything is still online. And if they have questions, well, they should write a message in the forum or in the Moodle online platform.
Right, right.
But with my PhD students, I do meet them in person. Yeah.
I see. So Prosenjit, maybe go online, or it's already.
It is already online because I made it online. Yes.
Okay. Okay. Yeah. So maybe Emil, we should check your slides if it is okay.
Yes, I think we did that already, but I can.
Okay, okay. Sorry. So that's perfect. Yeah.
Yes. So if you now see my slides, then we should be fine.
Yeah, it's perfect.
Yes, yes.
Yeah, this is perfect.
Perfect.
Yeah.
Perfect.
So Emil, we just wait for a couple of minutes and then we'll start.
Yeah, of course, no worries.
Yeah, thank you. So you want to also use Blackboard? I mean, some kind of, I don't know. You were mentioning you want to use on top of the slides something else.
I can use the tablet on the slides.
Okay.
I can write on the slides. Yeah, I hope that.
Okay. Okay. That is very nice. Yeah.
Yes.
So Prosenjit, just let me know when we start.
Maybe in 1 minute, at least 1 minute is left in my watch still.
Okay.
So you can start now.
Okay. Okay. So good afternoon, everybody, and welcome to today's session. So it's my pleasure to introduce our speaker today, Professor Emil Wiedemann from University of Ulm. So he did his PhD at University of Bonn under the supervision of Professor Laszlo Szekelydi. And currently, Emil is the director of Institute of Applied Analysis, University of Ulm in Germany. So his expertise lies in the broad spectrum of fluid dynamics, in particular application of convex integration theory to the Euler equation, in fact, which led to major breakthroughs in this field. So he has made several contributions in this field. So just to mention a few, he has proved the existence of weak solutions for the incompressible Euler equation, and also worked with the Young measures generated by incompressible fluid flow. So today he is going to speak on quick and measure valued solutions of the compressible Euler equation. So we are looking forward to this talk, Emil, and this platform is all yours now.
Yes, well, thank you very much. Of course, I would have preferred to be in India right now, which was planned, but of course, this is not possible at the moment. But I do appreciate very much that you set up this webinar series, which is, I think, a great way for everyone to stay connected and to keep up contact. So I'm really happy to be part of this. Yes, so as was mentioned in the introduction, I should share my screen. Yes, so this is the title of my talk. It will be about, well, somehow the relationship between weak solutions and measure valued solutions for the compressible Euler equations. And of course, I will explain the meaning of all these words throughout the talk. Just to point out that in the end, I will get to results that I obtained jointly with Dennis Gallenmüller, who is my PhD student here in Ulm. So the Euler equations look like this. This is the so-called isentropic compressible Euler system. So when I talk about compressible Euler equations, I always mean the isentropic system. This is a basic model of fluid mechanics that models a compressible fluid, like a gas, for instance, without friction effects. So later we will also see the viscous model, which is the compressible Navier-Stokes system. But for most of the talk, we'll be talking about an ideal fluid, which means there is no friction. So this first equation is just the conservation of momentum, which means that it's essentially Newton's second law applied in a continuum context. And this would be the mass conservation. Yeah. And we have a fluid velocity v and a density rho. And for most of this talk, I will consider the two-dimensional Euler system. So you can imagine you have two space dimensions, a fluid moving around in two space dimensions, and of course a time variable. And one often, this is not particularly important today, but a choice that is often made is the so-called polytropic pressure law. So the pressure here is a fixed power of the density, which means if you take the gas and you try to squeeze it together, then the more you squeeze it together, the more it you will encounter a force that goes against the direction in which you press the fluid together. So there is one very important physical quantity for this system, and you obtain it in a regular, in a standard way. So suppose you are given a solution, and that solution is, say, continuously differentiable. So you're allowed to perform the chain rule and integration by parts and so on. So then if you multiply the equation by its own solution, and you integrate the thing in space, and you do some computations, which involve, in particular, an integration by parts, then you will obtain the following conservation law. It is what you could call the energy equality, which means that the time derivative of this integral here is 0, which means that this thing is a conserved quantity over time. And this thing can be interpreted as the total energy of the fluid. So this here would be the kinetic part, 1/2 times mass times velocity squared. So that's the kinetic energy. And this part would be the well, the potential energy that you obtain, again, because the fluid is somehow squeezed together to various degrees. And the more it is squeezed together, the higher its potential energy will be. And this P is not exactly the pressure, but it's something related to the pressure. In fact, it will be, well, for the pressure law that I showed you, where P of S is S to the gamma, then this so-called pressure potential, capital P, will also be proportional to S to the gamma up to some constant that I forgot. I think 1 over gamma to the minus 1. But in any case, the pressure potential will be more or less the same thing as the pressure in this particular pressure law. So you see that this energy equality was formulated in a kind of global fashion because you have this space integral. But you can do similar computations without ever integrating in space, and that will lead to a bit more effort in the computation. But you will, in this way, get the so-called local energy equality, which looks like this. So you see, this is the integrand of the total energy, and this is something else, which is called the energy flux. And if you are familiar with hyperbolic conservation laws, you will kind of see that this is something like an entropy equality. So in the theory of hyperbolic conservation laws, one has the concept of entropy and of a corresponding entropy equality or inequality. And if you consider as a special case of a hyperbolic conservation law the isentropic Euler equations, then this is precisely the entropy, well, equality, or more commonly, you would have an inequality here. The point is that we are still assuming the solution to be smooth. But if the solution is no longer smooth, then these computations, in particular the integration by parts, are no longer justifiable, and you will lose the equality and get an inequality, which would then correspond to the second law of thermodynamics, broadly speaking, although not in the isentropic Euler equations, because there the entropy is conserved. Anyway, so I was already suggesting the study of weak solutions. You do that because you see that in the context of conservation laws, often the solutions will not be smooth. We will soon see effects like the formation of a shock wave, which means that there is a singularity, a discontinuity occurring in the solution. And so then the solution no longer will be differentiable, and therefore we have to work with a weaker framework of solution, which is what we call weak solutions, which is essentially the solution in the sense of distributions. And here is a definition. It looks very complicated, but what you do is you take the equation, you multiply it by a test function, and integrate in space and time and do all the integration by parts to get all the derivatives shifted away from the actual solution onto the test function. Yeah. So we have here a test function phi. This would be the momentum equation. And you see that, well, by integration by parts, we shifted the time derivative to the test function, and we did the same with the space derivative. In this way, we get this weak formulation. So even if you're not acquainted with hyperbolic PDEs, then if you've seen elliptic PDEs, of course, when you go through the theory of linear elliptic equations in a first PDE course, then you would also at some point define a weak solution using a test function and throwing the derivatives on the test function. And the same we do here. So we can do the same with the mass equation. And we can do the same with the local energy equality, only that now, since the solutions are no longer smooth, I might lose the equality and I get an inequality. And this would be the weak formulation of the energy inequality. So weak solution, so to speak, these two equations tell us that we have a weak solution. And this here is the admissibility condition. So this is really the standard concept of an entropy solution in the context of hyperbolic conservation laws. And we want to study these weak solutions. Now, people have studied these weak solutions, and the hope had been for a long time that a weak solution that is admissible is unique in, when you fix an initial data and you pose the Cauchy problem, then you would like to have a unique admissible weak solution. In fact, the idea that you would get a well-posedness theory in this class is motivated by the famous theory of Khrushchev, who studied scalar conservation laws. And for scalar conservation laws, indeed, you have a well-posedness and existence and uniqueness theory for weak entropy solutions. So people were hoping that this would also be true for systems of conservation laws, like the Euler system. But this turned out to be false. And the first counterexample was given here in a paper by Delelis and Sekehidi about 10 years ago. And then there had been more and more refinements of this theory. One important paper here is of Elisabetta Chiodaroli, and then they went on. And I would like to talk about a result of Elisabetta Chiodaroli with Camillo Delelis and Ante Kreml from 2015, because yes, they have an interesting theorem related to the Riemann problem. So what is the Riemann problem? You take initial data that is piecewise constant, and these piecewise constant initial data, they have a jump across a hyperplane, which in this simple case is given by the second coordinate. Yeah, so let me, and this is a well-known thing in conservation laws. So let me just briefly draw a picture. So this is kind of space-time, and the initial data is such that you have some constant state, say to the left of the origin, and you have another constant state to the right of the origin, and then you have a discontinuity at 0. And now what is classical in the theory of conservation laws and the theory of the Euler equations is that from this, well, very particular initial data, you get an admissible weak solution that kind of preserves this simple structure. So this is something like, which way is it round? I think it's x equals, so x2 equals sigma times t. Sigma is the speed at which this discontinuity moves. So you retain this structure of being piecewise constant and jumping from the left state to the right state, only that the location of the jump moves with the speed sigma in some direction determined by, well, the exact values of these two states. So this is known as a shock solution. You can imagine it as a shock wave that moves with a certain speed sigma in space. And this would be one solution, very roughly, that you would expect from this initial datum. So what these guys showed 5 years ago is that in addition to all these, in addition to this one solution that everyone knows and that is classical, the so-called self-similar solution, there are infinitely many other solutions. There are infinitely many admissible weak solutions in addition to the one that had been known. And this came as a big surprise, I think, to the hyperpoly community, because even for such a classical problem as the Riemann data, now you had infinitely many weak solutions. And for later reference, let me briefly say something about the proof. It has to remain on a very superficial level because I cannot talk about the convex integration construction here. But so what they introduced was the notion of so-called fan subsolutions. And a fan subsolution is a bit similar to Riemann data, only that somehow the initial datum, which consisted of 2 constant states, now fans up into 3 constant states. So sorry, let me just draw the picture once again. So instead of considering 2 constant states, now kind of I draw this, well, you could think from the picture of it as a fan, that's why it's called fan subsolution. You still have rho minus v minus in the left region and rho plus v plus in the right region, but here in the middle, you kind of introduce a new state. And this is called a fan construction. And this, of course, will no longer be a solution to the Euler equations. But it will be something like a generalized solution of the Euler equations, and the significance of this of this so-called subsolution is that by the kind of sophisticated convex integration theory that goes back to Delelis and Sekehidi, once you have a subsolution, you can start your convex integration construction, and this will give you infinitely many actual solutions of the compressible Euler equations. So the general idea is that you construct a subsolution, and after you have a subsolution, then the general convex integration theory will give you infinitely many weak admissible solutions to the Euler equations with the same initial data. Now you see that in fact, to determine the subsolution, you have to determine certain parameters here. So kind of the width of the fan, which is determined by these 2 velocities, nu minus and nu plus, and of course all these states in of the subsolution. But these are finitely many quantities. These are finitely many parameters. So if you translate the PDEs that determine the subsolution, I haven't defined exactly what I mean by a subsolution, but it's also a PDE problem. If you translate these PDEs into conditions for all these parameters, you will get just a set of algebraic equations and inequalities as far as the admissibility is concerned. And then, okay, it is a tedious but not very deep exercise to solve these algebraic equations to find suitable choices of all these parameters that will lead to the subsolution that you want. Okay, but let's step back a bit away from convex integration theory to ask the question, okay, do I want infinitely many solutions to the Cauchy problem? Well, this is a discussion I cannot really I cannot really give you a definite answer to, because some people say, well, yes, this is actually what we want to see. If we are serious about turbulence, then we know that somehow turbulent behavior does not behave in a deterministic way at all. So it's kind of natural to have an ensemble of solutions. So if you really want to stick to a deterministic framework and you want to talk about weak solutions, it's actually not that much of a big surprise that there should be infinitely many of them. So that's what people like Laszlo Sekehidi would maybe say. Other people who are maybe a bit more conservative would say, no, we do want a well-posedness theory for entropy solutions of a hyperbolic conservation law. So we want to find a selection criterion. This is something that has been suggested then after these infinitely many solutions came about, that yes, you want a criterion from all the infinitely many solutions. It should single out a unique one, preferably the self-similar shock solution, the classical one. And then what people often suggest is that you should take a vanishing viscosity limit, which means you introduce a friction, which is encoded here by a viscosity nu, and a diffusion term, an elliptic term here in the velocity. And this is known as the compressible Navier-Stokes system. The point is that the existence of weak solutions is known to the system, at least for certain adiabatic exponents that are greater 3/2. This is a famous theory by Pierre Lilians and then later Eduard Feil-Reisel. And the idea is, well, formally, if you let nu tend to 0, formally you would obtain again the compressible Euler system. Although it's of course a highly non-trivial and non-obvious question whether any weak solution of a sequence of weak solutions of the compressible Navier-Stokes would converge to a weak solution of the isentropic Euler. So why is this a difficult question, this viscosity limit? Well, it's a difficult question because we don't have enough compactness. So what we can do is, according to the a priori estimates for compressible Navier-Stokes, we get certain bounds in LP spaces which allow to extract a weakly convergent subsequence of solutions of the compressible Navier-Stokes equations. And now if we pass to the weak limit and we want to see if the weak limit is a solution to the Euler equations, we get into trouble because nonlinearities and weak limits do not commute. Again, let me illustrate this by writing something down. You can see this in a simple way. Of course, you know that in one dimension that something like sine of nx would converge weakly to 0 as n goes to infinity. This is the paradigmatic case of weak convergence. You have oscillations at higher and higher frequency. And so this would be some n, and this would be a larger n. And this will converge weakly to 0. But if you take a nonlinear function of this sequence, say you take the square of this sequence of functions, then it will converge weakly in this case, yes, but not to 0. So in this sense, the nonlinearity, which is the square function here, and the weak limit will not commute. So the square of the weak limits is not equal to the weak limit of the squares. And you have a similar term in the equations of fluid dynamics. So you have always this advection term, which looks like a quadratic nonlinearity. Also, you have the pressure term, which is nonlinear, and so on. So this is the reason why you cannot simply pass to the Euler equations in the weak limit. And this is where measure-valued solutions come into play. So one trick somehow is one trick to somehow linearize the problem is to identify the solution, the elements of your approximating sequence with a probability measure. Yeah. So suppose for every nu I have a solution rho nu v nu of the compressible Navier-Stokes equations, and I have and I do not consider it as a function from x and t, but I consider it as a Dirac probability measure that sits at the position rho nu and v nu in state space. Yeah, so this Dirac measure here is a probability measure on the set of possible states rho and v, and in addition, it is dependent on space-time, on x and t, which means that it is a so-called parametrized probability measure. Now, if you take the weak star limit of this sequence of probability measures, you can define a weak star convergence in the sense of probability measures, including the dependence on x and t. And you can pass to the limit, and you will get some kind of limit object. Now, the limit object will be a parametrized probability measure, but it need no longer be Dirac. Yeah? And the interpretation is that this probability measure here, if you freeze space and time, gives you the probability distribution that the density and velocity of your solution are such and such. So this is called a measure-valued solution. It gives you the probability distribution in state space, and you lose a lot of information because unlike the deterministic description through a weak solution, you cannot say, okay, at this point in space-time, my velocity is exactly like this. You can only give a probability distribution for it. So that's the concept of such a measure. And now, if you just do the weak limit in the sense of probability measures, and you take the expectations of the quantities in question, say here that this would be the advection term, this would be the density. You take the expectation after passing to the limit under this limit Young measure. You will see that you get to a system of equations that resemble the Euler equations. And of course, if I use this suggestive notation, it looks like we have a solution of the Euler equations, but one should be careful. In principle, I just swept the problem under the rug, because the problem is, for instance, here, that rho v times v bar meaning integration with respect to the parametrized measure, will in general not be the same as rho bar v bar times v bar. And this is exactly the problem about commutation of weak solutions and nonlinearities. You know? Okay, so this is the idea of a measure-valued solution. And this is this again is the definition. Whenever I have a probability measure that satisfies these equations, recall that these equations here depend only on the parametrized probability measure, and it's called a measure-valued solution if it satisfies these equations here together with the measure-valued version of the energy admissibility criterion. And this definition of measure-valued solution is independent of the question whether or not the measure-valued solution is produced or is generated in the way that I use to motivate it from a vanishing viscosity or any other approximating sequence. Yeah. So the definition of a measure valid solution is only that it satisfies these equations here, plus maybe the energy admissibility. Now, there is a motivational question somehow, because, this concept of measure valid solutions was introduced in the 80s by people like Di Perna and Maida. And this concept has often been criticized because somehow after passing to the weak limit in the sense of measures, you will have lost a lot of information. And in any case, the really tricky problems about compactness and weak limits versus nonlinearities, you kind of just bypass these problems. So it seems a bit like cheating when you work with measure valid solutions. But in the past years, this concept has gained a lot of interest again. And I think this is due to several developments. So one thing is that it became known that although this concept is such a weak kind of solution, then still you have so-called weak-strong uniqueness principle, which means that if you have a smooth solution of the Euler equations, then any measure-valued solution with the same initial data will coincide with a smooth solution. So you don't have uniqueness, but you have at least weak-strong uniqueness and weak-strong stability. And this kind of weak-strong stability principle has a lot of known applications, say to the long-time behavior or to singular limits, even to numerical analysis. So this has been very useful in a lot of cases. A second reason why people want to study measure-valued solutions is, that somehow if you conduct numerical experiments, you will find that upon a slight perturbation of the initial data, for instance, for a shear flow situation, you will never recover any kind of stable weak solution, but the statistical quantities that you can express with measure valid solutions, they will be very stable under perturbation and in the numerical simulation. So this is something that Fjordholm, Mishra, and Tudmore, they ran a lot of numerical simulations. And they came to the conclusion that somehow to capture what they saw in their numerical experiments, the measure-valued framework seemed much more suitable than the classical weak solutions. Mm-hmm. And another reason why somehow measure-valued solutions are maybe not just as weak as a solution notion as you might have thought, is the following result that I obtained in the incompressible context together with Laszlo Szekehidi. So what we proved is that you can take any measure-valued solution and you do not know beforehand whether it is generated from a sequence, from a viscosity sequence or from a sequence of weak solutions. But then you can construct a sequence of weak solutions of the incompressible Euler equations that generate or approximate in a suitable sense your measure-valued solution. So the slogan of this theorem that we proved could be described as every measure-valued solution can be approximated by a sequence of weak solutions, which means that the measure-valued framework is not much weaker than the weak framework after all. Yeah, so all the things that people had been saying, measure-valued solutions, there's too many of them, you lose too much information, it's much too weak of a concept, it contains almost no information. So all these worries that people had are in fact not well justified, because in the end, weak measure-valid solutions are not a weaker concept than weak solutions after all. And this is now, I see that I'm using a lot of time for the first half of my talk, but I was told that there are some master students who have not do not have very much of a PDE background. So I choose to go very slowly here, and let me use the last 10 minutes to describe a bit of the research that we did recently. So yeah, so the question is now, can we obtain a similar result as the one with Laszlo Szekelyhidi for the compressible Euler equations? Well, I would have to, let me just present the results. Yeah, so these slides here are just meant to motivate a bit the method that we used, and I want to skip this because I have very little time left. So let me just come to the results. Well, okay, let me at least say something about the wave cone. Yeah. So what you do when you when you look at these convex integration constructions like the one that I presented at the beginning of the talk is you somehow, well, I do have to go back at least to explain this, is to kind of linearize the equations. I don't mean linearize in the sense that you probably know linearizations. It's actually something much simpler, and it looks pretty stupid. But you take all the nonlinearities in the equations and you replace them by new independent variables. For instance, for what was originally called rho v times v, you just kind of set that to be m. No? And now you look at this system in isolation, so you forget that it came from the compressible Euler equations, but you just look at this as a system of linear differential constraints. Of course, the system is highly underdetermined because you threw away all the nonlinearities and replaced them by new independent dummy variables. I wouldn't see that as a system of linear PDEs, but rather a system of certain constraints that do not fully determine, of course, this state vector consisting of rho m, capital M and Q, you know, kind of extended state space. And for such linear constraints, you can conduct a plane wave, so-called plane wave analysis, which is also a rather simple thing. So there are certain directions of oscillation that are permitted by these linear constraints and others are not. Yeah, this is the notion of wave cone. The wave cone is the set of all directions in state space in which I can have plane wave solutions. So you have the state vector z bar, and you have a scalar function that depends only on one direction of space or space-time. And this will give rise to plane waves that are compatible with these linear constraints. And the wave cone is the set of directions in state space that are compatible with the wave cone. Now, let me skip these examples. But the thing is that you can explicitly characterize the wave cone. And in the spirit of compensated compactness, which is a theory developed by Tartare and Murat and others beginning in the, I think, 1970s, you can, you can obtain a following kind of rigidity result. So you can say, if I have two states that are not, whose difference is not in the wave cone, so these two states are not compatible with the linear constraint, then I cannot have oscillations between these two states. Yeah. So the way I explained it, it seems obvious. Yes, the way I introduced the wave cone. These are the permissible directions of oscillation, and so if I'm not lambda connected, then I cannot oscillate, and this can be made rigorous, and this is our rigidity theorem here with together with Dennis Gallen-Müller. Now, yeah, as I said, the interpretation is a sequence that complies with the linear constraints cannot oscillate between these two states, and our result is a generalization of previous work, mostly the rigidity result of Ball and James in a very different context of elasticity, and a few other remarks that are maybe not so important. And one way to apply this to the question at hand that had to do with Euler is, okay, I can come up with two states in the generalized state space of the Euler equations that are not lambda connected. And now I do something very easy. I take as my probability measure just a convex combination of these two states. This does not depend on x and t, so in a trivial way, it is a measure-valued solution of the compressible Euler equations, but this cannot be recovered by a sequence of weak solutions, simply because if this measure were generated by a series of weak solutions, then these weak solutions would have to develop finer and finer oscillations between these states Z1 and Z2, which is ruled out by our rigidity result. Yes. So this is the easiest thing you can do to answer the question. It shows, yes, there are measure-valued solutions that are not approximated by a series of weak solutions. But here, okay, we cheated a little bit because, well, this is a constant measure-valued solution, meaning in particular that its initial data is a non-atomic probability measure. It's a convex combination of two Dirac, so it's a non-atomic probability measure. And you could say, well, it's not very surprising if I even start with not with deterministic initial data, but with a kind of superposition of very different initial data, then I cannot get this effect. I cannot see this effect by a sequence of weak solutions. So you could say here I cheated a bit. So the more interesting question, so this is just what I just said to you. The more interesting question is whether I can see the same effect with atomic data. Yeah, and this is something then that is the main result of our work with Dennis Gallen-Müller. So we were able to come up with atomic initial data. So you start with deterministic data, and we found a measure-valued solution that cannot, with this initial data, which cannot be recovered by a sequence of weak solutions. Yeah, and this means that the compressible Euler equations in this respect behave much differently from the incompressible Euler equations. Yeah? For the incompressible Euler equations, we have this result that every measure-valued solution can be approximated by a sequence of weak solutions. And here, for the compressible system, we find that this is not the case. So this is a real difference. Now, what we can show in addition, this is kind of, yeah, also follows from our rigidity result, that this measure-valued solution that we constructed does not even arise as a vanishing viscosity limit. Yeah? This is a different question. So I could not ask, okay, do I get it as a sequence of weak solutions of Euler, but do I get it as from a sequence of weak solutions of Navier-Stokes with a vanishing viscosity limit? And we also see that this measure-valued solution is not a vanishing viscosity limit. So I think this is also an interesting observation because, and this is the first remark down here. It indicates that the measure valued solution that we constructed here should be regarded as unphysical because it does not arise as a vanishing viscosity limit. So this relates to a very important discussion that is going on in fluid mechanics. Well, and it relates to what I said in the beginning, that people are thinking of a vanishing viscosity limit as a selection criterion. So we have a lot of solutions, we have infinitely many solutions, but the vanishing viscosity should single out only one of them. And here we have really a situation where we can prove that we have some kind of solution object, yeah, the measure valued solution, which we can safely discard as non-physical because it does not arise as a vanishing viscosity limit. You know? So I think yeah, I would like to consider this theorem that we have as a contribution to this ongoing debate on the question of selection. How can I determine which of the many solutions that I have to the Euler equations are actually admissible in the sense that they come from a vanishing viscosity sequence? Good. I think this is all that time permits. So I thank you very much for your attention, and I'm looking forward to your questions.
Okay, so thank you, Emil, for this wonderful talk. So now I request all the participants to type their questions or comments in the question answer box. In fact, I see a couple of questions. So do you see it, Emil, or should I actually?
I'm just trying to open it. Mm-hmm. But yeah. Okay, but I don't see any questions right now.
If you go to question and answer, Q&A, so there is a logo.
Okay. Q&A.
I think at the bottom of your screen there should be.
Yeah. It's here it's called F&A because somehow my language settings are German, so it's Frage und Antwort. Yeah. Anyway, I found it now. Okay, so I see two questions here. So the first one, let me read out the question first before I try to answer it. Since convex integration theory confirms that entropy solutions are not unique, what, in your opinion, should be the correct notion of solution in order to establish well-posedness theory for the compressible Euler equations? Yes. So this is a very good question that has been asked in the community for several years now, and well, obviously there is no no real answer to it as of now. So okay, I think indeed the best candidate for a selection criterion, and the one that is most popular in the community, is the vanishing viscosity limit. It is not known whether many of these infinitely many solutions arise as a vanishing viscosity limit, and many people believe that if you are not a vanishing viscosity limit, then you certainly are out of the game. Yeah? A solution that is not a vanishing viscosity limit should be deemed inadmissible and should be kind of kicked out of the discussion. Now, as far as rigorous mathematical results in this direction go, there is not much to say, unfortunately. Yeah? So there are a few results in very particular examples, and mostly in the incompressible setting, that tell you, okay, that there are infinitely many solutions, but only one of them comes about as a vanishing viscosity limit. but due to some technical reasons, I think that these results are not really convincing. On the kind of negative side, maybe you have heard of the papers of Bookmaster and Vicol, who constructed, in fact, infinitely many distributional solutions of the Navier-Stokes equations, incompressible Navier-Stokes equations. And as a corollary, they obtained that, in fact, every weak solution to the incompressible Euler equations is a limit of weak solutions of the Navier-Stokes equations. So that would be, again, a kind of negative answer to your suggestion. Although these viscosity solutions they do not come from a Leray-Hopf sequence of Navier-Stokes. So you could also say that these are not real solutions of the Navier-Stokes equations. But okay, to summarize what I said, yes, what you suggest, that there is a selection criterion, this is believed by many people, and it's believed by many people to be the viscosity limit, but there are very few rigorous mathematical results in this direction. So the situation is, kind of unsatisfying at the moment. And the other question that Sarah is asking is intuitively, why can't we emulate the analysis for incompressible Euler to compressible Euler? So I think this question relates to, well, we have our result, our characterization result for measure-valued solutions for incompressible Euler, and we want to know it for compressible Euler. Why is this question, what is the additional difficulty in the compressible case? I think at the core is the different role that the pressure plays. So in the incompressible fluid mechanics, the pressure is only a Lagrange multiplier. It is not, so to speak, a variable, an independent variable in its own right, but it's kind of a Lagrange multiplier. And in the weak formulation, you project it away by testing against divergence-free vector fields, and the pressure disappears and you never care about it ever again. In compressible fluid mechanics, the pressure plays a much more rigid role. You cannot just simply project it away, but it is a given function of the density, and in this respect, it is an honest independent variable, an honest unknown of your system. And this means that in the compressible system, because the pressure is now a more rigid quantity, the wave cone about which I talked becomes much smaller. So the incompressible system somehow gives you the opportunity to oscillate in many different directions, because you can always adjust the pressure to allow the velocity to oscillate in this direction. But once you consider compressible fluid dynamics, then you cannot simply choose the pressure as you want, but the pressure is somehow something that is a rigid part of your system, and due to this additional rigidity, your wave cone will become much smaller. Yes, so in a sense, the compressible system is much less flexible than the incompressible system, and this gives rise to the additional difficulties. Okay, next question, please, if you were so kind to repeat the naturality to consider measure-valued solutions. Yes. So measure-valued, why do you consider measure-valued solutions? Well, there are many ways to motivate this. One way, as I said, is that you do not usually have the appropriate compactness to pass to the weak limit in all these nonlinearities. So you pass to the limit on a different level, no longer on the level of solutions, weak solutions, but on the level of parametrized probability measures. And I think engineers or physicists would refer to this process as what they call coarse graining. Yeah. So in a sense, you take a small region of space-time and you consider you consider averages of your fluid over such a small space-time region. And if your well, fluctuations, your oscillations are of sufficiently fine scale, then the averaging process will kind of average out these oscillations. And the object that you obtain after this averaging procedure is exactly the measure, the parametrized probability measure. So that is one way to see the measure valued solution. So it has mathematical significance in that you can get measure valued solutions, although you do not have the existence of weak solutions. And these measure valued solutions at least satisfy some nice properties like weak strong uniqueness. So on the mathematical side, this would be one way to motivate the use of measure valued solutions. And secondly, on the physical side, it corresponds to this procedure of coarse graining, and it gives you at least certain average quantities of your fluid that are of interest. And this relates also to what I said about these numerical computations of Fjordholm, Mishra, and Tadmor, that in fact, in a turbulent fluid, a lot of what you can see is stable or predictable only in a statistical sense, and there the measure valued solution seems to be the more natural object to consider. I hope that answers your question. Yes, the next question is how do the existence results compare to da Fermat's entropy minimizing criteria? Well, that is also a very good question, because the only, well, selection criterion that I mentioned so far was the vanishing viscosity limit. But as you say, there has also been the suggestion of da Fermat's to consider the entropy minimizing or maximizing criterion, where the idea is that among all entropy solutions, among all solutions that dissipate entropy in the mathematical sense, yeah, because physical entropy should increase, mathematical entropy is minus the physical entropy, so that should decrease. And the rate of dissipation of entropy should be maximal. So this is a kind of sharpening of the second law of thermodynamics that da Fermat has suggested. It says that entropy should not just dissipate somehow, but it should dissipate in the fastest possible way. And it is interesting to see that in certain examples, say for shear flows, the selection criterion suggested by da Fermat gives rise to different solutions than the selection criterion that comes from vanishing viscosity. So for a shear flow, the vanishing viscosity limit would be just the classical solution, the stationary solution. But if you look for a solution that dissipates energy or entropy at the fastest possible rate, you would get one of these wild solutions that come from convex integration. Again, there are not many rigorous mathematical results in this direction. I think there are examples by Chioddaroli and Kreml showing that somehow de Fermat's entropy minimizing or maximizing criterion does not single out a unique solution. The problem is that kind of you don't have a maximal element. Yeah, so in certain convex integration constructions, you can, well, for every weak solution that you give me, I can give you another weak solution, admissible weak solution, that has an even faster entropy dissipation rate. So as far as I know, there are examples or constructions that show that de Fermat's criterion does not give rise to a unique maximally dissipative solution. But I do find the concept interesting, again, considering turbulent flows, because I can imagine that somehow, well, somehow the wild solutions coming from a shear flow initial datum actually are more realistic than the stationary solution, which is highly unstable. And those solutions that, well, satisfy the Fermat's criterion to a higher extent, they would correspond more to the scenario that you actually physically observe.
Okay, so thank you. So I have got another question in my chat box. It says that is it possible to extend your result to compressible Navier-Stokes equation? If yes, then please give some hint. If no, why?
Yes. Well, as far as the construction of like non-unique weak solutions goes, there has certainly not been any result for compressible Navier-Stokes equations. Even in the incompressible setting, this has been very recent. It's the celebrated work of Buckmaster and Vicol that I mentioned. So for compressible Navier-Stokes, actually, I don't know if some kind of adaptation of the Buckmaster-Vicol procedure would also work in this case. I haven't looked into it, and I don't have the I'm not so familiar with the work of Buckmaster and Vicol that I could say from the top of my head that that their construction would also work in the compressible setting or not. And as far as the characterization of measure-valued solution goes, well, first of all, measure-valued solutions are not considered as much in the Navier-Stokes setting, because for Navier-Stokes, you usually, at least for sufficiently large adiabatic exponent, you know the existence of weak solutions. And if you know that there are weak solutions, classically, then there is not much motivation to study measure-valued solutions. You know? But okay, even in the regime, say gamma is less than 3/2, even in this regime where you would consider measure-valued solutions, the relation between measure-valued and weak solutions is very difficult to characterize, because also in our result with Dennis and in the previous result with Laszlo Szekelyhidi, we always relied on some form of convex integration construction. And as long as the convex integration is not available for compressible Navier-Stokes, then I think also this measure-valued analysis will not be possible.
Okay, so thank you, Emil, for this wonderful talk and also this answers to this question. So thank you.
Thank you very much.
Okay, so for information on next day's talk, so I would request Prosenjit to provide all the details. Thank you.
Yeah, thank you, Professor Emil, for this wonderful talk. So I have one announcement to make to our participants, to all our participants. So this announcement is being made for safety purpose. So I just want to say that if there is some trouble happens between a talk in future talks for then I request you all to visit our webpage immediately. So this is the immediate action that we should take. That will be the way of communicating with you. Okay. And so for next week's talk, we have Professor Shougata Bandyopadhyay from ISAR Kolkata. And we'll see you all next Tuesday. And I now request everyone to leave this platform. And thank you all.
Okay,
Thanks.
ciao, Emil. Thank you.
Bye-bye.
Bye. Okay, so I'm disconnecting the talk, the session now.